Hi, everyone. Again, welcome to the HAI Research Seminar. I'm Deep Ganguly. I'm the Director of Research at HAI, and I'll be moderating today. A few house rules before we get started. The chat on Zoom is disabled for now. If you have questions for the speaker, please visit the Slido link shown in your QR code via mobile, or you can go to the HAI events webpage to find a link. And I'll be watching those questions come in. And after Chris is done speaking, I will be sort of fielding those questions over to Chris. And that's it for house rules. So moving forwards, I'm pleased to introduce Professor Christopher or Chris Ray. He's an associate professor in the Department of Computer Science at Stanford University. He's in the Stanford AI lab and is affiliated with the Statistical Machine Learning Group. His recent work is to understand how software and hardware systems will change as a result of machine learning, along with a continuing and petulant drive to work on math problems. Those are his words, not mine. And research from his group has been incorporated into scientific and humanitarian efforts, such as the fight against human trafficking, along with widely used products from technology and enterprise companies, including Google Ads, Gmail, YouTube, and Apple. He's co-founded 4 companies based on his research into machine learning systems like Samba Nova and Snorkel, along with 2 companies that are now part of Apple, Lattice, also known as Deep Dive in 2017, and Inductive, also known as HoloClean in 2020. His research contributions have spanned database theory, database systems, and machine learning, and his work won Best Paper or Test of Time awards at premier venues in each area. And he still cannot believe he won the MacArthur Foundation Fellowship. So without further ado, take us away, Chris.
Deep, thank you so much for the introduction. I really appreciate it, and I'm excited to chat with you all today. This is going to be fun. Hopefully, you can now see my slides. So, what I wanted to talk about today are some of these higher level abstractions for machine learning and some of the new challenges that they bring. So the first part of the talk will try to be concrete about this pretty vague topic, which I'm going to call software 2.0, and try and give you a sense of why I'm excited and why I think there's something interesting going on here. And then try and make it concrete for you of why these things look different. And then what I'm going to plan to do is talk to you about some of the challenges in the second half of the talk. Things that kind of worry me, keep me up at night, and are driving a lot of our research. And I've opted for fresher research topics rather than things that are a little bit more established. But first, let me give you a little bit of context. So when you think about AI or machine learning, you probably think about individual kind of small products like translation or medical imaging or robotics. These are really exciting. And you think about the quality that those bring to their respective areas, which are really, tough, hard problems. But there's something else going on under machine learning and AI that's really interesting and fascinating to me, which is you have this huge productivity change. And it's, a crude measure, but you look at this kind of lines of code of old systems versus new systems. The old Google translation system was 500,000 lines of C++ code, very traditional code that we would teach an undergraduate and still teach an undergraduate. But the new versions of these systems that are state of the art are only 500 lines of code. And they're 500 lines of what's called data flow code, a different programming model than we've been used to, because they're powered by these machine learning systems. And this has let people actually take a bunch of problems that were kind of classically hard problems and start to apply machine learning to them, not just these kind of translation and medical imaging, but starting to the nuts and bolts, how you tune your systems, how you tune your networks, how you do data cleaning. And this is just a random sample. There's a lot going on in this space. Now, when you have these kind of changes, you may think, if I'm talking about these software 2.0 changes, we're talking about something that's really on the horizon. It's kind of out in the future. But, when you started talking about it in 2016, that was the case. We didn't know, we kind of sensed something was happening. We didn't know what was happening. But one of the most remarkable things with our collaborators is that actually this stuff is already getting used. These are things that are collaborations with our lab or with folks who have come out of our lab. That are products that you've probably used. If you search on your laptop or web search or an assistant or Gmail or YouTube, this new style of how you design these systems is already around you. And that transition from kind of being lab ideas and weirdness and just kind of malformed thoughts to actually something you can use in your hand has been staggering to me in the last really only 3 or 4 years. So I think it's not because we did such amazing jobs on these things. I think it's because we really identified an interesting need. Now, one group that deserves a lot of credit here are the Snorkel folks. They've spun out as a company now. They were in the lab. They spun out as a company led by Alex Ratner and a bunch of folks that were there. They've gotten really far advanced from the research side. So if I talk about the research, it'd be kind of talking about what we were doing in 2018, 19. They've gone much farther, lots of companies using them. The key insight that they had is that actually a lot of machine learning and AI platforms are really data first, really about the training data. That's how you get the expertise into the system. That's where you manage it and monitor it over time. And they're off and running. So those systems I just described were really based mostly around kind of Snorkel ideas. But what I want to talk about, as I said, was kind of this fringe, kind of what are the principles that are underneath what's going on to try and understand what's next. And I'm going to admit, it's fuzzy and it's weird. And I'm going to try and make it, as concrete as I can. But I hope through our conversation, we both get a little bit more understanding of what's going on in this space. And I'll try and share with you why I find it so interesting. So one bit here, and this is true both in industry and academia, and I think people don't really appreciate it that much, is that models have become a commodity. So when people build AI systems, they often, 5 years ago, we would focus on the models. We would build software to help us build models. But now you can go and download these models kind of anywhere. And so yes, there's still research to do in models. We're writing papers about models, for various different research conferences, but they'll probably show up in Hugging Face if you're doing NLP or in a GitHub repository relatively quickly. And so if you think about when people who are applying this, which is the vast majority of people who are not researchers, innovating in models is kind of not where they're spending their time. And that's true even in very, very large companies. That's not where they're spending their time. So where are they spending their time? Well, they're spending their time on something which is important for them, but is also, I think, really interesting for AI and interesting for the reasoning aspects of AI. And so I'm trying to articulate this. I don't know how to do it quite precisely, but I'm kind of calling it fine-grained reasoning and quality. Now, what I mean by this is if you've been following AI and machine learning, you've seen these mega models come out that are so awesome, and they do so many impressive things, right? Now, in some ways, of course, if you boil the web and you see something 100 times, our machine learning tools should be good enough to pick it up and recognize it, right? Recognizing that those two things are the same 100 times, that's really challenging. But where the challenge is, where these models still fall down, and also where I think the most interesting work is going on, is in what I call the tail or the fine grain aspect. And this will be a theme throughout the talk. So for products, this is the battleground. Kind of everybody can get the head and torso, that is, the most popular queries that are asked by an assistant or the most popular things. They should be able to get that right every time, right? That's actually, understood. We know how to engineer that. The battleground are in subtle interactions, subtle disambiguations of terms. And we'll talk about that a little bit later in the context of products. For AI, it's interesting because to be able to handle those places where your data is sparse, humans fall back on reasoning. We fall back on knowing the types and how they interact, and do people have heights or brands have prices? We know things about the world, as we'll argue, and that allows us to reason in some of these cases. And so I think for research and kind of an interesting point of view, it's also really interesting. So this is why we're kind of thinking about it. And everything you'll see in the Software 2.0 piece, you'll see that it's really about, in the HAI mold, it's about humans at the center. It's about trying to get those unnecessary barriers where people who have domain expertise but have difficulty, kind of teaching the machine about it. We want to remove all those barriers. And even for people who can do it, who will focus on first, that is, who can teach the machines, we want to make it as easy as possible and focus on the part where their unique creativity and the things that they find interesting and impactful are something that they can do easier, and kind of automate out everything that can be automated so that they're more interesting and impactful as a result. Okay. So as I said, we've been working on a bunch of different systems since 2015, 2016. I mentioned Snorkel earlier and Samba Nova, which is basically that idea that everything's data flow now. And so what if you built a silicon processor system software from the ground up? You would do it differently if you knew everything was going to be data flow. You're going to be faster, more efficient, be able to handle larger models. That's kind of the Samba Nova story. Snorkel I mentioned before. This is, if you think about what are you going to build in an AI application, well, it's very different than the old applications, as I'll talk about in the next slide. But what I want to talk about are Overton and Bootleg today, which are two fairly recent papers that have come out, kind of high-level papers that have come out about how we're building these systems. Both happen to be in production, but I'll try and highlight for you what's interesting about them. And so the reason I'm focusing on production, I decided is, if I wanted to leave you with a message, I want to say we're in the early innings of kind of a new discipline I hope forming. And that's this AI engineering discipline or ML engineering discipline. And I think, borrowing from some of our other friends in the area, this is not my idea alone. Machine learning has been kind of a fundamental technology like chemistry, but we need a department, of folks thinking in terms of chemical engineering. That's what we've done. In the same way, we'd love to have folks who are thinking about AI and thinking about what are the engineering modes, what is the kind of math to make these robust, what are the abstractions that help us build that. And I'm really excited about participating in that kind of work. So the first claim I'm going to make here that, hey, maybe this is actually new and different, and that these require radical systems is a software 2.0 claim here that I'm making. And it's sort of a subtle point, but for example, one of the things that you could imagine you would do is we know how to build search, or we know how to build assistants. We know how to build various different pieces. We have architectures for them. And typically these architectures are kind of boxes and arrows. You do X, then you do Y, then you do Z, then you return the answer. And I'll give you examples of those later. In these systems instead, you'll see what we're doing is changing the boxes. We're not taking machine learning and putting them in the existing boxes. We're changing which boxes are even present. And that means we have to do some kind of new engineering, some kind of new principles that didn't come out of the systems principles that we previously had to build them. Okay? Kind of a very high level claim. The other claim, which I'll be able to be much more concrete about, is that AI systems have new failure modes. And so what I'm going to show you are places where folks make surprising errors, not due to adversaries. People are really worried about adversaries, and that's good. I think those are exciting. But I'm very worried about the people who, with the best of intentions, still have horrifying bugs or mistakes, especially in medical applications. So that's something else we've been working on. So what I'm trying to convince you is that really we need a theory and practice to maintain and understand these systems and make them robust over time. And we're really at the first innings of that. And I'll share some of the work we're doing here, but we're by no means alone. It's just, I think, where the field, I hope, is going. Okay. So the first thing I want to do to be concrete is show you one of these systems. This is a system we wrote, a couple of years ago, but just became public. And it'll kind of sense the conversation of the arc of what I saw in AI that biased my work and kind of put me in this position where I'm talking about maybe these crazy ideas. Okay. And again, I don't speak for Apple here. Okay. So I wanted to change the conversation. So the story goes, basically, they acquired my company, as Deep said, my first company, and I looked around and I kind of wanted to change the conversation about where machine learning systems and how they were being built. So we kind of have to go back to 2017 and say what was going on. And if you remember this time, basically people were, looking on archive every day, looking at new models. It felt like every day a new model was coming out. And as a result, people were trying to implement them at kind of a feverish pace to keep up. Now, in 2017, an interesting paper came out that was starting in the same direction that I'm talking about, that I was really excited by, and now is just, kind of a classic in the field, which was this attention is all you need paper. And basically it was a model that was called Transformer. And what it basically said was that for a lot of different models, you could actually use this single building block again and again and again to build them at a high level. This is much more technical than that. And so this was a much more important transformer than, the Michael Bay movie from that year. Now, even though this paper had come out in 2017, teams had not adopted this. They hadn't seen this as a conceptual advance. And, it was brand new. But they had this problem that I would call kind of new modelitis. So a machine learning team would say, I have a new problem, I need to build a new model. And what I'm trying to warn you off is I say that's kind of, in my mind, an outmoded way of thinking. And then they would spend months implementing it, and then there would be no improvement. And if you were looking at this as someone who was kind of an engineer or who had built these systems, you'd say, well, kind of obviously the model isn't your problem. Understanding your data, understanding your application, that's the problem. And if you looked at teams that were performing well, they were spending much more time in that latter bucket than they were spending on writing new models. So I started to look at these best ML engineers who are around Apple and Google and other folks that I was interacting with pretty routinely. And I would say, these folks who really measure their system and understand it, they were still suffering. And so what I wanted to do was basically show that you could automate all the parts of their jobs that they didn't like, right? That's where infrastructure, I think, comes in, where, there's things that were holding them back from being creative and putting those insights into the system. And so I started to look at all the pieces that I thought I could automate. And this is where one of our first software 2.0 systems, which is the system Overton, came up. And maybe if we're lucky, we would prevent new modelitis. So the goal was really a high-level goal, was to shift the conversation from building models to really monitoring quality and improving supervision. You say, why monitoring quality? Well, in these services, humans are asking questions. Humans are there are errors that are coming in. You're looking at these things. You want to understand what's changing about the world. What insights do you have where the assistant is performing poorly or something? You'd love to be able to understand and deal with that in some way. And this is something that all systems face. So I went around with a slide deck. That's what professors do. We make slide decks. So I go around with my slide deck and I say, hey, this is a great problem. We should start working on it. Here's some ideas about how it could be better. And I think, if it's possible, fewer than 0 people listen to me as a result of that. And so I said, okay, we'll have to start writing some code. So I sat down on my couch and I just started hacking and started to build a prototype that I wanted to say, let's start a conversation and say, hey, we can do something that looks like this. And I had some, just amazing friends and, colleagues who were really supportive and gave me a ton of feedback and started to have conversations about the code. And what was shocking is it actually became a production system that as far as I know, is still in production. It's been in production for years, and it's, pretty exciting. We wrote this small thing. And what it speaks to is the need, not the quality. I'm a professor, it's professor code, but it just speaks to the fact that there's something you can do here that's different than what people were doing before. And at least some people will find it valuable. Not everybody, not every need, but there's something going on. Okay, so this is a high level what we were trying to do. What are the technical challenges? Let me go one level lower and then we'll pop back up. So when I mentioned those pipelines, those old style systems, this is how you built some of those systems, classically. If you look into the literature, you take a course. If someone asks a question like, how tall is the president of the United States? Well, you kind of think about it in a pipeline. You first find the named entities. Oh, we're talking about the president of the United States or president and the United States here. We're asking how tall, that's called the intent. So we're going to go and try and build a machine learning model that tells me how tall is someone, and that model does its job. And then we actually have to do some inference to say, oh, it's not talking about the office, it's talking about the person who holds the office. Oh, and probably now, not a couple of weeks ago, right? And then once you do that, you fire it off into the query and you return the answer. Okay? So each one of those boxes was kind of implemented by a classical pipeline and usually by an entire team of people. And then each stage would have an error that would kind of compound potentially. And if I had only known what the intent was, I could have done a better job at named entities and so on. This was kind of the classical software 1.0 way of building even machine learning products. So the 3 challenges, one is these pipelines were complex. And if you look at a lot of the errors, my guess was a lot of them were seams between products. Individual products that an engineer does, we know how to build pretty well. We're at that stage, which is exciting. 10 years ago, nothing worked. Now things work, but they work in little pockets. They don't work, holistically in the way that we hope, in the kind of holistic intelligence that we want. The other thing that I noticed was it was super hard for people to share ideas. If you had an insight in one part of the organization about how to deal with complex disambiguation for sports teams, and you wanted to share that with the people who were in media, it was very difficult because these pipelines were really complicated. Another thing was that what they were cared about was monitoring really fine-grained interactions. These are things which in the log you could look at were extremely rare, but they were important. Because they were kind of, when you talk to someone and they say 10 things you agree with and then 2 things that are crazy, you think they're crazy. Not that you don't give them credit for the 10 things they know. And so even if you start to have these assistants that are around all the time, you persistently see the problems that they make. And so these rare but important interactions were fine-grained. It was like needles in a haystack that these teams were kind of finding, which is an interesting state to be in. And the last thing was their job and what they cared about, those best teams, was improving quality. They weren't interested in models, but they had to build models to do their job. And so it was kind of an interesting thing. They also were really worried about deployment, as I'll talk about. Now, this has led me to some potentially really contentious claims. The first is that engineers should not set what are called hyperparameters. It's a waste of time. These are the things that you don't have, these are table stakes, you can do them inside everything, but you'll see engineers constantly spending their time tweaking these little values. There should be no margin for this, so no system should allow them to do this. Model architecture is not really a challenge. Although the transformer is all you need, or the attention is all you need as they described, actually a fair number of models will get you the quality that you want. That's not where the challenge is. And you can wrap those on top and just pick which one of a handful of different models. You don't have to do really fine-grained search over very fine details. There really are coarse-grained building blocks that work. That's one potentially contentious claim. And the last bit is there's a split that happens in most systems where one team writes the model and builds it and figures out how it's supposed to do and injects their insights, and another team takes it to production. And that's really, I think, harmful because when you have a bug in production, you don't know if it's because of the changes the production people made or a bug in the original model. And those would be some of the most contentious things. So these were things that I wanted to get rid of in Overton. So I'll just show you an example of Overton at a very, very high level. So it wants to handle updating the supervision, but it's going to handle training the models. It's going to handle model search, and it's going to handle model deployment. So just to dive one level down, this is your first Overton program. You can look in the paper, there are more complicated things. In fact, an entire production service effectively fits on one, part of one page, which is a real production service, basically, with just small elements redacted, their program. The two elements are a schema that tell you what's in the data. These are the payloads and tasks on the left-hand side. And the right-hand side are many records, which are the examples that it's being fed. The payload describes what's in this, the schema describes what's in the payloads. So for example, these tokens that have a type sequence, they say that there's a tokens field and it has, the entry of the query, how tall is blah, 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 okay? The schema allows Overton to build data stores for training, for inference, separate all the input types, basically take all the pieces that you need to build the pipeline. Those are all commodities. It's going to go build those for you. It also describes simple data flow. You can make this more complicated, but tasks. So for example, this is saying that you want to take in those tokens and you want to classify them into various different tasks. So parts of speech, just as a simple example. And the idea here is that you're just describing the tasks that come in and the data that's there. You're not saying anything about the model. I won't go into too much detail, but also as Snorkel pioneered, you can use weak labels. So one major challenge in these systems is reconciling truth. So you could have many different voters, if you like, throughout your system that say what the right answer is. You have to resolve them, or you have to inject domain knowledge, which is only approximately correct. And basically Snorkel handles that for you. The important point here, as you see, is that you're saying what you want, not how to get it. And another way to say this is that the key is what is not required here. There's no mention of a model. There's no mention of parameters. There's no mention of traditional code. And as my buddy Piero Molino, who wrote this wonderful system, Ludwig, which I'll talk about a little bit later, he called this zero code deep learning. And I think this is a really fascinating way to program, and you can actually build production services based on top of this. So the other thing that you do is you can tag examples. And this is because people really wanted to be able to monitor in a fine-grained way how their model was doing on those rare interactions. Okay. So what does Overton do with this information? A bunch of low-level stuff that you probably don't care about. It preps the data for training. It builds data structures that can feed GPUs, that can feed into the bindings and production edge services. It does all that data prep for you. It combines the supervision using ideas like Snorkel and data programming to make sure that it has its probabilistic and best guess of truth. It takes that description and it creates a TensorFlow or a PyTorch program, the low-level ways that people program these machine learning models today, and it picks all the model parameters for you. And then it creates a deployable model that can be deployed in a variety of form factors and generates a huge number of quality statistics. So you may look at this, and when I first started talking about this with ML engineers, they'd say, well, where do the engineers spend their time? So, well, they spend their time monitoring the quality and improving supervision. And that's the whole point. Rather than spending all those things that they could automate, could they spend the time that require human understanding? What's going wrong? Why is it going wrong? What information does the system need? Not what data structure should I feed the GPU? That's not something that really engineers really should be worried about. And so this may sound crazy, and you would worry, would people actually use this? And I would say some machine learning teams actually have no engineers writing those lower level frameworks like TensorFlow or PyTorch. And potentially this changes who can write these models and who can deploy them, which is super exciting to us. Now, the other thing you say, oh, well, you're going to get lower quality. Those people were monkeying with models because when they did all this fancy stuff with their models, that was what was going to generate quality. And I would say not so fast. These are error reduction numbers, and they're pretty outstanding in terms of when the software 2.0 style things were deployed versus the old thing. And resourcing here refers to how many engineers are on the team. Roughly tens of engineers, sort of 10 to 20 engineers is medium, and under 10 is low, roughly speaking. Had big error reductions when they converted to these models. And the reason is simple. You're making better use of human time, right? The reason that Google folks really love the weak supervision approaches is they would have cases where they would deploy a system with a weak supervision approach before the other one got off the ground. That's really Snorkel's particular genius, which we borrowed in some way here. Okay. So related work, as I said, Ludwig, check out Ludwig. It came out of Uber. Piero Molino is a genius. I looked at his system after I had written Overton. I wish I had seen it before. He would have saved me a lot of time. He did a much better job than I did, just like a real artisan. I cannot tell you how impressed I am with that stuff. And we became buddies because I became such a fanboy of his. Andre Karpathy, who's a wonderful PhD from our lab, who's now super famous at Tesla. You probably all know who he is. Wrote this wonderful post, Software 2.0, that I really just loved. And I think it's worth reading. Very different perspective from what I'm talking about. Snorkel, as I talked about, was everywhere here. And of course, this wouldn't be possible without just amazing investment in TensorFlow, PyTorch, CoreML, all these tools that have really just changed the landscape. Okay. So the point is that Overton's goal was to move engineers up the stack. And I just want to point out that the tools have really changed, and they've changed what people need to do to specify them. And so this key is focus on fine-grained tail quality and supervision. So let me talk a little bit more about the tail, and that'll get us into some of the problems that come up in these systems. So as I mentioned, a key challenge here is the tail, and I'm going to talk about the system Bootleg, just the problem, not the solution. You're definitely welcome to check it out. As you'll see, it's done by super smart and fun folks. So it's got a great cat who's apparently a rum runner. Laurel made that logo, and I absolutely love it. So these are the folks who did it. Simran, Neil, Megan, Chow, Laurel, and Sen really built this thing, and it's super cool, and it is in production. So the idea here is you want to do named entity disambiguation. So someone asks you, how tall is Lincoln? And you have to map Lincoln the string to Lincoln the database. And it's a key thing you have to do in assistance, search, information extraction, kind of a foundational problem. So, there's several Lincolns it could be the car company, could be Lincoln, Nebraska, could be the president, but only one of them has a height. So it's obviously Abraham Lincoln. Now, the thing that gets interesting about NED, as we've talked about, this named entity disambiguation problem, is the tail. So lots of people have mentioned things about Washington, D.C. Probably every question you've wanted to ask about Washington, D.C., someone has asked somewhere online. You just need to find it. Probably the same thing's true about Chevy, about Corvettes too. Reddish potato beetle, I'm not sure that every question that someone would come into someone's head is somewhere on the web. And if you look this song, my students make fun of my love of emo rap, the song Sauce by XXXTentacion, like it's not even in the database. No one even knows about it. And the point is that those things that are rare, that are out there, that are popular, the standard techniques, models work well. The rare ones, those are the ones where these models start to fall down. And the majority of entities are actually rare, which is a weird way to think about it. But if you look at query logs across any of the large companies, the amount of queries that are unique in a 3-month time frame is the overwhelming majority, absolutely overwhelming majority. If you look at Wikidata, for example, fewer than 1% of songs show up there. So a lot of your information is in kind of these weird databases that are scattered across the web. And it turns out that to do this kind of subtle reasoning in the tail, this is where AI systems, I think, get really interesting. And as we'll see, it's about a 40-point gap. Okay? So I'm going to go through this very, very quickly. We built a system that was kind of hands-free. I invite you to check it out. Here's an example. Although they toured together, Lincoln did not take its name from They Might Be Giants' album Lincoln. These are different Lincolns. That's Lincoln the band. That's Lincoln the album. How did we know that? Well, the band here, Lincoln, was mentioned with They Might Be Giants. So if we know They Might Be Giants is a band, then because they're kind of the same type and it took its name from it, we could infer that, yep, that's Lincoln the band. And then album is in a positive phrase, right? Album Lincoln, that's a relatively easy one. So we built a system that did English when I was at Apple. We had to scale it out to a bunch of locales. So we realized that we could never possibly scale this by engineering them by hand. So we basically built these systems that read Wikipedia and web logs and try to understand automatically, to whom, about whom you're speaking or what you're speaking. Okay. And the hint here is that we're going to have to be able to make use of structured information. Things like we know something's an album, we know it's a band, we know who's in the band, all those kind of clues, and I'll defer to the paper. And so I just want to flash up here, it's not a Joker system, it sets new state of the arts. What I'm saying is not like, some weak comparison baseline. But the thing I want to highlight, and this is really, really critical to kind of what we're going to do next, the tail is the game. So if you look here at unseen entities, for example, and these are a little bit out of date numbers, you see that the Bootleg system is almost 40 points better than the, BERT, which is the state-of-the-art baseline. It was a classical baseline. However, if you look at the overall numbers, because they're so biased to popular entities, it's only two points better. And the reason I'm bringing this up is if you don't measure carefully, you will think your system is doing something interesting, but it's not actually. It's just kind of recapitulating things it's seen a bunch of times. And that to me is really fascinating about how to build these systems. So the problem we have is how the heck do you understand, how do you slice up your data? So I want to plug a system here with our good friends at Salesforce and UNC called Robustness Gym. And the point is that basically what Robustness Gym gives you is a way to slice your data really finely and compare systems and understand various different things like, hey, on Bootleg, how well does it do on resolving NFL players or teams in sentences? And you can slice that and see, oh, Bootleg's doing pretty well here, but Microsoft's not doing as well, Google's not doing well. And so this allows you a tool and a mechanism to start to get more principled. It's early innings. We're going to try and automate it and do things, and we're building it now. So if you have use cases, please reach out to Karan, my student who's kind of leading the effort. We're trying to build lots of stuff in here. We're going to have workshops. But again, what it's about is trying to build tooling that helps humans kind of dig through the needles in the haystack. All right, so with that kind of priming, hey, these things are a challenge in the tail. I want to talk a little bit about some of those new challenges that come from these higher level abstractions. And I'm going to do a detour to give you context and tell you a story. So the story starts with basically us working with a bunch of radiologists. My students were, Alex and a postdoc, Jared, who did a remarkable amount of work here. And those other folks are physicians. You can see the physicians like to wear ties, the computer scientists, no ties. So they were working on this problem in radiology. And we didn't invent the problem. People were talking about it a lot, especially in 2018, 2019. So the problem is, people take a lot of radiographs, but actually sometimes they're not looked at. And the reason they're not looked at is the relevant expert, just isn't there. So they collect the image hoping that they'll look at it. And then they try to make their best guess sometimes without it. And it's not me saying this. I don't speak with any authority on this. These are things that people publish about, that these radiologist shortages are actually leaving patient care at risk, which is pretty interesting. So we thought, this is amazing for machine learning. The bar is super low. We just have to be better than not looking at the image. This is something we could help with. Like, wouldn't that be awesome? Let's go and try and build it. And so we said, we'll build a deep learning system to do this. And so we asked, would it actually help us? Would it be better than that bar? And it turned out it was really not an easy question. There was no benchmark data set. The effective data quality was unclear. There was no assessment of existing algorithms. And the algorithms that were out there had no feedback from the clinical community. And this is one thing I especially think for HAI folks, this integration of communities, absolutely critical to making progress on foundational AI questions, as well as impacting the world. So now, as a result of this, I should say, some of those folks in ties, they put out an awesome data set. You should definitely check it out. But back in this time, it didn't exist. So Jared spent a year, all of 2018, basically trying to answer this. He created a large data set of clinical labels, went and talked to clinicians, figured out what they were talking about, evaluated the effect of label quality, and most importantly, he published it in a clinical journal so that we could make sure that our findings were really reviewed by the community that would care about it most. One thing to reinforce what I said earlier about models being commodities, this DenseNet 121, if you're a machine learning AI nerd, it's a super popular model, Killian's model from CVPR Best Paper 2017. Awesome paper, great model. But the difference between that and this model at the top, which you could have comfortably trained 15 or more years ago, only 2 or 3 points on these things. But remember what we saw at Bootleg, 2 or 3 points can be misleading. Is that 2 or 3 meaningful points? Or are those 2 or 3, damaging points? Let me give you a moment of pause, because with Bootleg's priming, you probably think, oh, those are really good points. Well, let me say, maybe, let's look at it a little bit more closely. So these eyes haunt me. What do these eyes have to do with it? Well, any model that we build, deep learning or otherwise, is built because we can't write down the signal precisely. If you knew exactly what you were looking for and precisely how to describe it, you should just write Python or C code, traditional code. The reason we use machine learning is because it picks out signals we didn't quite intend or were just too difficult for us to specify. These deep learning models are just that on steroids, which is awesome. They pick out more unintended signals and do things that we love. So what do these eyes have to do with it? Well, those eyes, were something that these folks were doing where they were trying to look at the iris and they were trying to predict the gender. And I don't even know if this is biologically plausible, but what they noticed is their methods weren't transferring from one data set to the other. And then what it turned out that they were picking up on had nothing to do with eyes, but actually was picking up the mascara, which was in this wonderful paper, where they showed actually that the confounder that they had not controlled with, hey, there's some mascara on there. And as a result, they predicted the gender with some higher than chance accuracy. So this gave me a lot of pause. And I said, do we know how well these models are really performing? And I got super nervous, and I was giving keynotes about this, and I would always bring it up. People would say, oh, well, maybe it was just kind of a mistake. It wasn't systematic. And it just kept eating at me. And then when I looked at Jared's work, I thought, are we so sure that those 2 to 3 points are really causal or anti-causal? How would we know? And it really started to eat at me. And so we started to talk about it a lot more. And then, as the great thing about being Stanford for faculty, you just get to complain about things that you don't like or you don't understand, and then smart people figure them out. In this case, these are the smart folks who started to figure out, hey, what's really going on here? And they wrote this wonderful paper, which is called Hidden Stratification Causes Clinically Meaningful Failures in Machine Learning for Medical Images. They're real physicians and scientists. They use long titles, not like us. Okay, so it's not just those eyes, turns out. So here's an example of dermatology. So what you're looking at is a lesion there, and then what you see below it is what's called the heat map of where the model is looking. Eventually, that's basically saying like, what is it paying attention to most in the image at a very high level? Here's another case that it's looking at, and there happen to be these two purple dots. Those purple dots indicate that you're going for surgery, and you notice that the model ignores the lesion nearly entirely and only focuses on the purple dots. And why not? If it sees the purple dots, it's got a leg up that it's actually melanoma, it's actually skin cancer. It didn't just happen there. If you look at things like lung detection, this was a very hot topic, looking for collapsed lungs called pneumothorax. I can't tell the difference between these two images, no matter how many times I look at them. When they ran it through the model, though, the model was superhuman, 0.87 AUC, superhuman, better than the radiologist, awesome, very exciting. It turns out, however, that the image on the left has no drain, and the image on the right has a drain, or so I'm told. The problem is when you have a drain, that's anticausal. It means you're being treated for a collapsed lung. So with chest drains, which mean you're already treated, if you remove those, then all of a sudden it goes from 0.87 AUC down to 0.77. And that gap is tremendous. As as Ben Rack from Berkeley tweeted, it's going from, superhuman to worse than a first-year resident. So it's a massive gap as a result of this. So now I'm terrified at this point. I think, how the heck are we going to stop these things? And so what Jared and co looked at is that there's this one problem, there's many problems, but there's one problem underneath the covers. There's a subset or class they identified that was performing worse. So what was happening is you were labeling things as abnormal in the images, but no one thought to distinguish purple dot versus not, or drain versus not. It didn't occur to them when they were doing the labeling. And so there's a subpopulation that has the drain and a subpopulation that doesn't have the drain. And you do dramatically differently on the parts that don't have a drain. If you got every drain one right, that would be fine. But you really happen to care here about the without a drain subclass and doing poorly there. So this happens all the time in medical imaging because we kind of cut off at a higher level of abstraction what we know. It also happens in these systems because you would never write in an old style system, a mechanically defined system, software 1.0 kind of system. You'd never write something that says, if there's a drain, then classify as pneumonia or pneumothorax, right? You'd know you were cheating. If there's a purple dot, then cancer. And it's not that these systems are bad or malevolent or the people who did them are weird. It has much, much more to do with this idea that when you go higher level, you just bring in new bugs. So we started to think about this problem. Could we develop a theory and a host of associated techniques to start to understand this hidden stratification problem? And we're in the early innings here, but I'll share one exciting result with you. So this is a problem called No Subclass Left Behind, done by this cast of amazing characters, and it was in NeurIPS this past December and online. And these folks were really smart. So their observation was that DeepNets were learning features that could distinguish between the subclasses, even if they were trained on coarser models. So remember going back to that Killian Weinberger's genius DenseNet architecture that we loved, that was doing 2 to 3 points better. Somehow it turned out that more sophisticated architecture was actually, according to our tests, learning actually to separate out those classes. We just kind of had to help it and amplify it. And so what we would do is we would train a neural net model. We would try and bias it to push apart the feature space so that it would try and cluster there. And we would be able to see what you're seeing here is there's a case where you have patches and no patches, and you want to make sure that they're treated the samely, those subpopulations. And it would kind of push them apart in space. The red and the blue, it would try to do it. Now there's still some red and blue on top of each other. We didn't do a perfect job, but we pushed them more apart. And then what we would do is we would kind of hallucinate. Even though we didn't know the subclasses, we would say there's subclass A and subclass B. We didn't need to know what they meant semantically. And then we would train a more robust model that said, hey, you need to be robust and not be differential on red and blue. You should have about the same accuracy on them. That is, you shouldn't depend whether you have a drain or not when you do this. And what was pretty impressive here is that it improved the accuracy on the worst performing subclasses by about 22 points in one example. This doesn't mean it's going to work everywhere. We're, again, first innings. And what we described here was a set of very simple assumptions where you got the same per class generalization as you would get if you knew the classes, right? So if you even here, there's some conditions that we're trying to understand where those deep learning models actually will sufficiently separate out because they're doing amazing things under the covers that allow us to actually be safer to generalize than we would have been with the older style kind of deep learning or automatically learned methods. And so to me, this is a really optimistic bit, which says that, a lot of this progress that we're doing, we're actually starting to see at these fine-grained kind of quality level, but we're not there yet. So in conclusion, what I wanted to talk to you about today is that there's this weird new thing that's happening in software. A lot of software is changing. Models are becoming commodities. Training data is not a commodity yet. Monitoring is not a commodity yet, but models really are becoming a commodity. We talked a little bit about kind of how these horrible errors are easy to make. And we're at the first stages. Can we do something with them? Can we actually figure out, hey, here's what's going on underneath the covers and try and separate them out? And there's some optimistic stuff that's going on. These new models actually do seem to be kind of interestingly robust. They do seem to be able to go more into the tail, but there's a lot to do there. So when I talked earlier about, hey, what does it mean to go finely into tail and get those fine-grained errors? You've seen a couple of examples, fine-grained examples in the labels, fine-grained examples in the log where you're trying to answer, sophisticated disambiguation. There's a lot going on here that we can unpack. So with that, thank you so much for your time and attention. Look forward to talks. Please feel free to email me and ask questions. I'm a high latency and low bandwidth as an email responder, but I do try to get to absolutely everything. And I really appreciate any thoughts and feedback. Thanks so much.
Thank you, Chris. That was a phenomenally interesting talk. So to the rest of the audience, if you haven't chimed in on Slido, check the chat link for the link to that if you want to ask any last-minute questions. And with that, I sort of have a burning one for you, Chris. So you made a lot of claims about sort of how engineering workflows will change in the transition from software 1.0 to software 2.0. So for example, you said engineers should not set hyperparameters, model architecture is not really a challenge. Getting a model ready for production is not really a challenge. You even mentioned zero code deep learning. So there are a lot of comments in the chat that were of this flavor, like how will the shift from software 1.0 to software 2.0 affect the skills needed by programmers?
Yeah, I think this is absolutely a wonderful point. And the first answer is we don't know. We're at the first stages, but I can share with you what I've seen in some of these places in different kinds of engagements. So you're seeing a shift both driven by the Snorkel folks and driven by the Overton folks. And I'll try and share some examples from each. From Overton, it was pretty clear to me what happened. What you ended up having is you had even people who were hardcore machine learning, AI, paid to do that. They were so focused on their production systems that they stopped writing those particular low-level code and started being able to diagnose what was going on. Now, one thing is they were experts. So it was actually easy for them, if they kind of saw a mistake, to understand and kind of hypothesize why this mistake was actually happening. So they were experts and had a kind of a very different balance and interaction. So I don't know you would want to change the skill. It was kind of co-designed with the humans that were there to evolve. But what you saw were that you saw teams that would be relatively small be able to handle many more products. So it used to be like per product, per locale, you would kind of have a team or have an assigned manager. There's one, Pallavi, who's there, who's amazing. Everyone in the world should know who she is. She was on that paper. She managed a huge number of products effectively with like half of her time. So that change was pretty radical. And so as a result, more humans were deployed on these harder, thornier questions. So it's just a question of waiting, I would say there. In Snorkel, I think it's more interesting in some ways. Snorkel is a full AI platform of how you inject domain knowledge. And so when you talk about the skills that are involved, they're very rapidly creating, use case based and other workflow based things around subject matter experts, around business users, around folks who are driving it. And so it's bringing a different ecosystem. And we've seen things happen like this before in computing. If you look at like when the relational database came out, that was a long time ago. But pre-relational database, so I'm told, from reading, is like everyone was writing their own little system of how they manipulated their data. They had their own custom application. Everyone was wiring it all together. Then you impose this beautiful layer and between it, and then all of a sudden applications above could flourish and people below could flourish. Storage systems could all flourish. So it's not that work stopped there. Of course, there's been amazing work in storage and databases for the last couple of decades. It's just that that wedge point opened up everything. And so the hope is that, you ask what kind of, skills going forward are valuable. It's going to be the same critical thinking skills that never goes away, right? Like that's the main and important thing. Its domain expertise becomes even more valuable. Like the thing that I always thought was a terrible asymmetry in these models are people who could do tricks. I would call them kind of statistical tricks. And those tricks were valued more highly than the people who understood what was going on. And I hope to reverse that over time. Anytime you see an asymmetry like that, that's a failure of computer science. We should always make it so that the people who know what they're talking about are empowered to do more, not the people who know how to play the game internally. And so that's the hope of the trajectory that we're going on. We're not there yet, but that's kind of the general sense. Very, very insightful question.
That's fascinating. That seems like a world I want to get to sooner rather than later, right?
Yeah, one hopes. I don't know how far away we actually are, but
right.
yeah, but it seems nicer. Yeah.
So a somewhat related question, like, in software 1.0, again, we're starting to see a rich community spring up around issues about bias, which can be in the training data, it could be in the model representation of the data, and then can have somewhat pernicious downstream effects later on. You could imagine this happens in software 2.0 in unexplored and possibly unknown ways. So to what extent have you guys been thinking about how to think about those issues in software 2.0? And can you tell us more about that?
Oh, I mean, what a wonderful question. And yes, I mean, it couldn't be more on the minds of everyone in technology and computing, right? Now and hopefully before too. I hope it's not newly on everyone's mind,
right.
But it's certainly at the fore right now. So in one sense, let me say something a little bit strange. In one sense, when we looked at Snorkel originally, we had a kind of an expletive moment where we were like, oh my God, what have we done? Because we were like, hey, you're creating a team that injects systematic bias into the system. The way Snorkel works is that people will write and codify down rules to label data and we'll extrapolate from those rules. But somehow we've given you a tool that allows you to amplify, biases. And so we were terrified about that and started to think about it. When we saw it deployed, we saw two things that were interesting. And it's too early to say anything really positive here or negative. But one of the things that we saw is that if you have to codify why you're making a decision in a distinct way, that's a little bit of a stronger record than the way traditional machine learning systems are trained. With traditional machine learning, someone makes a judgment, yes or no, they never tell you why. Mm-hmm. In a kind of software 2.0 Snorkel universe, they have to explain their reasoning a little bit, and that could be auditable, right? That could be something that's on the side that says, hey, here's the schema, here's the list of rules that annotated this data and made that decision. Where's the bias that's there? This eliminates potentially one form of bias, which is kind of like accidental or unintentional bias in the annotator that's kind of creeping its way systematically into that. There's a second kind of bias, which is the really pernicious bias that you said, which is, we're starting from biased data sets. And if we start those from those biased data sets and we feed them into these systems, they're going to reflect and worse amplify that bias. Now, one of the things I'm excited about there is that, if we look at these systems that actually do kind of reasoning patterns or controlled reasoning patterns, I didn't get to talk about it in Bootleg, you can guide how it reasons. And we want to understand and fix those issues. It's a major problem in production systems. There's a certain class of bias that people care about, which, attract, media attention, candidly, that people are trying to fix, and they get an undue result as a result of that. And that's wonderful, by the way. I should say, having been on the receiving end of the complaints, hey, the system did X, Y, or Z that, we think it shouldn't be doing, please send those. There's that's making the world a better place. So do that, because it will force people to have the pressure to clean these things up systematically as we see them and develop the tools. But if you force folks to reason again at a higher level, they can't rely on some of those clues that you don't want them to rely on, those spurious correlations, those biases that they're picking out in the data set. It's not a panacea. It is certainly far from solved. But that's something we've been thinking about, quite a bit. And then the last bit is, as you mentioned, when you have these differentially treated subpopulations that we were talking about in hidden stratification, and can you help and identify that there's something that's different about this population, even if you didn't think about it ahead of time? Because there's two models you can imagine of bias creeping into these systems. There's one model, which I would call kind of, an intentional model, and I hope doesn't exist, where people are fine with the bias being there. That has never been my experience with tech folks, to be candid. I've not met someone who's like, let's make our system, racist, misogynist. No one wants that in their system. It's not something that's there. But of course, they're not aware and they don't have the tools to address it. And so this understanding the representation that I talked about, we've thought a lot about how that ties into just amazing work that's gone on in the fairness and accountability and transparency communities, where people are starting to look at how do those biases come in and how do they link up. And so that how do you deal with those differential subpopulations of groups are really intimately connected. So as you're seeing here in Software 2.0, the issues aren't going away, but hopefully again, if you, and maybe this is just, I have maybe not tech utopianism, but, colleague utopianism. If we're able to get, this into the hands of folks who are equipped to talk about those conversations, have those conversations, to identify those systematic systematic biases, to identify those pernicious issues earlier and more directly. Maybe we disintermediate the fact that it's got to go through tech people who make sometimes ill-founded claims like the algorithm can't be biased, the data can't be biased, really evading their central responsibility in the systems that they produce. So I'm hopeful that happens, and we got to keep doing it. But it's definitely on all of our minds, especially given that role that we have, that privileged role of shaping the training data, which is exactly what's feeding and being reflected in these systems.
It's fascinating. I mean, to some extent, that kind of calls back to something you said earlier. As you put more decision-making power in the hands of the domain experts, perhaps they're also better or more equipped to sort of identify things like hidden stratification or biases in the data. Or
exactly right.
Yeah.
The more information that we can get out of the folks who really know and understand the domain, every machine learning person should really be on a quest to fire themselves as quickly as possible. You want to get out of the way of the people who really understand, because you're building a horizontal tool that can positively impact the world, but it doesn't positively impact the world in your hands, right? Mm-hmm. I had to be, you mentioned in my bio, I got to work on this human trafficking thing, and it was a great honor to work with those people. I didn't solve any of those problems. I solved pretty boring machine learning problems when you looked at them, but the folks I worked with and the folks they worked with tried to understand the places in which we could do that. And that's something that really inspired me, because it made me realize we were giving them relatively simple tools when we started, and they were making an unbelievable impact. That's going to happen all over computing. The next phase of computing, computing really has always been about trying to make other people successful. And if we understand that and get out of our own ways and stop thinking about, how are we making tech successful? How are we making the world successful? That's a better anchoring, I think. And it's just a place where we're gonna get to. And so I'm hopeful a lot of these, and I don't want to say that and say like abdicate responsibility, like, oh, we're gonna wait for, people, ethicists to come in and tell us what to do. No. We need to make sure that we're having these conversations. And it's one of the reasons when you folks were firing up HAI, I was so excited about this thing. We had tried in various forms to get these collaborations going throughout campus, and having a central place was just, really exciting for me personally, and I think the campus overall.
Oh, I must say I completely agree with you.
That was a point that I thought would be really super contentious, Deep. I didn't know if we were going to have to fight about that one. Sorry.
Well, we can fight in private, maybe. So speaking of ethicists, here's one according to my internal named entity recognition system that I think might come from an ethicist, which is, if the new goal in the 2.0 model is to move to measure quality and improve supervision of machine learning systems, like, what is the benchmark for measuring quality, and how do you even identify such a benchmark?
What an amazing question, and it gets right to the heart of the issue. And my answer here is, we don't know what quality means in a lot of ways. And so when we started to look at it, we realized we would have these systems that had multiple stakeholders throughout the organization. And I'm familiar with the industry side, but the same sets of characters would be present in any other organization as well, where you would have folks who are from marketing and brands and other products trying to understand, what does this quality of the system mean to me? Right. And so we started to try and build these tools. It's what this robustness gym was about, to try and say, can we even identify and track them over time? So one thing I think people outside the field believe about machine learning, which is unfortunately not true, is that we have a real knowledge of what our systems are doing. We have a frightening lack of clarity of what they're doing. And I think when people say that, they immediately gravitate to the mechanistic understanding, like, do we know what every neural network layer is doing in the model? And I think that's important, that's interesting. People can work on that. I don't actually work on that. What I prefer to think about is, can we understand what its output is, characterize its behaviors, and try and understand kind of those pieces. And so when you come to a multifaceted question like quality, concretely, I mean things like, the precision and the recall. How often is it correct? How many answers does it miss? But when you start to think about quality and fluency, that's where things get really interesting. Summarization, that's something that's in this robustness gym project, and we're trying to understand and elicit it, but make it push button so that my notion of quality and your notion of quality, we can at least compare and contrast. Because I think what the questioner is getting at is, the idea of an absolute objective notion of something so sticky as the quality or fluency of translation has in some ways held back the field, right? I think Chris Manning has these great papers. There's this blue score that all the translation people rant about, say, oh, we can do better. But still everyone uses the old score because everyone knows how to compare it. And they keep coming out with new scores, but they're all different. And so I think we have to kind of have tools that embrace those differences and allow people to at least see them, highlight them, and then weirdly enough, track them over time, which I think if you talk to my colleagues who are not tech people, they'd say, oh, you're not doing that already? And I'd say, like, shockingly, no. Like we don't have tools that do that automatically. So we have to get some of that blocking and tackling to be able to ask these deeper and more interesting questions.
That makes perfect sense. And I should say this might be a good plug for HAI. We are sort of through this AI index report are tracking a performance over these well-defined benchmarks over time. It's a very manual kind of job, but it's super interesting to see performance. One thing that happens is that you saturate the benchmarks pretty quickly in some cases, like in glue and super glue.
Those things come out and they're kind of solved right away, but then you try to use the models and they're not working as well as you would expect.
Exactly.
And I think one of the things that we've seen and why we try to do this is when I was talking about the battleground being these finer and finer granularities, that's where we start to see these models actually perform differentially on different subsets. They get a high overall score, but they actually fail making interesting decisions. Or, the very common cases where they use the background as a spurious feature to get all the examples they've ever seen correct, but they don't look at the foreground, what you think they're doing. And so I feel like, one of the reasons we wanted to put up these kind of robustness systems was to facilitate researchers and industrial folks comparing their systems kind of more holistically and not reducing them to a single kind of point and benchmark number. That was the impetus for the robustness gym. I wish I had a more satisfying answer because one number is way more satisfying. It's super easy to say you're doing well or poorly on. But I think the other side is we've been misled in some ways. I don't mean intentionally, just unintentionally, these numbers create a bias where we think we're doing sort of better than we are. Because you look at these systems and you say, as I was talking about in the log, we as humans have a tough time thinking about these tail distributions where it's like, okay, we actually get, 85% of everything we've ever seen, we answer correctly. Well, no one cares because they think that's table stakes. And every once in a while, someone's asking a different question that's not in that 85% and you get it wrong. That 85% accuracy doesn't feel so good, especially if they're asking enough questions. And so I think those issues have been kind of throughout the field. Also, you mentioned the index. I love the index effort. Yoav and folks, I hope Yoav's still involved. He's involved in the first generations. Tracking those efforts is really important. I think, both the internal facing efforts of, hey, how are we doing on the benchmarks, but also externally, where is it starting to be used? And I think the thing that you saw when Yoav was first, kind of talking about these things was, hey, internally, we're seeing a bunch of use, but externally, we're not as far along as people may think. Like, I think right now there's a belief that the big tech companies, they've been using magical machine learning in all of their products for the last 10 years. False, absolutely false, right? It's very early. And so when I look at companies and I look at folks who are doing research, like, you're not that far behind, right? You can't possibly be decades behind, right? It didn't exist. And so that transition has been very, very rapid. And the hope is, because so much of this is open source and done communally, more people can participate, which is one thing that AI kind of magically was able to do, which is, as I said, the reason models are commodities are because people aren't hoarding them and thinking, is Google's model better than Microsoft's model? People kind of know which models everybody's using. And what an amazing thing that that's happened. And the tech companies deserve a lot of credit for that, for actually participating as researchers in the community, which is wonderful.
Yeah. Well, okay, so we're at time. So I think with that, we'll have to stop. To the audience, thank you so much for tuning in. Thank you for the wonderful questions. I'm sorry I couldn't get to all of them. And then to Chris, really thank you. This was a super interesting talk and really awesome ideas. And really thank you for joining us today.
Thanks so much for having me. I appreciate it.
All right. So take care, everyone.